3 rows of humming hardware racks. This server room is the physical heart of the Corporate Local Area Network, or LAN. It houses proprietary source code, internal financial ledgers, and thousands of live user credentials. To protect that data from the outside world, engineers secure the digital perimeter using Wide Area Network, or WAN, encapsulation. This diagram illustrates the 2 ways PPP verifies a connection. On the left, PAP, the Password Authentication Protocol, uses a weak 2-way handshake that transmits the password in vulnerable cleartext. On the right, CHAP, the Challenge Handshake Authentication Protocol, uses a secure 3-way exchange. It verifies identity using a randomized challenge and an MD5 hash, which is a cryptographic fingerprint, meaning the actual password never travels across the wire. When this connection runs over standard broadband lines, Internet service providers use PPPoE. Point-to-point protocol over Ethernet wraps these serial connection features into standard Ethernet frames. It establishes a session using a strict 4-step discovery phase: initiation, offer, request, and session confirmation, or PADI, PADO, PADR, and PADS. A properly configured WAN perimeter is mathematically secure. An attacker on the internet cannot break through that outer gate, so they bypass it entirely. They walk into the building and strike from the inside. A visitor plugs a tiny rogue device into an unguarded lobby wall jack. They are now inside the physical perimeter. This diagram shows what happens next. The attacker launches a tool called MacOff, flooding the switch with thousands of spoofed hardware addresses. This triggers a CAM table overflow. The content addressable memory is the switch's internal ledger mapping media access control, or MAC, addresses to specific physical ports. When this table hits maximum capacity, the switch panics. It degrades into a basic hub, blindly broadcasting all network traffic out of every single port for the attacker to read. Next, they starve the network's IP address pool and stand up a rogue DHCP server. The Dynamic Host Configuration Protocol is the system that automatically assigns network addresses to devices. By controlling this, the attacker assigns their own machine as the default gateway, intercepting all outbound traffic. To capture internal traffic, they broadcast gratuitous ARPs. The Address Resolution Protocol links a network IP address to a physical MAC address. By poisoning this routing cache, the attacker physically bends the legitimate data streams between internal workstations to flow directly through their machine, establishing a perfect man-in-the-middle position. Now they move toward the high-value data by injecting a fake DTP frame. Dynamic Trunking Protocol is a Cisco feature that automatically negotiates a link to carry traffic from multiple networks simultaneously. This tricks the lobby switch port into becoming a trunk, allowing the attacker to hop directly into the secure server VLAN. A virtual local area network logically isolates groups of devices, but the attacker has bypassed that isolation entirely. Here, we see the attacker broadcast a priority 0 BPDU. Bridge Protocol Data Units are messages used by the Spanning Tree Protocol to map the network and prevent data loops. By claiming a priority of 0, the attacker forces the protocol to elect them as the new root bridge. The entire network hierarchy collapses and redraws itself around the rogue device, triggering a devastating 30-second communications blackout. Finally, they target the users. A single phishing click from an employee executes a silent payload called Hook.js. This is a cross-site scripting, or XSS, attack, leveraging the Browser Exploitation Framework, known as BEEF. It grants the attacker persistent remote control over the employee's web browser. In under 60 seconds, the attacker flooded the switches, hijacked the routing, breached the secure servers, and compromised the endpoints. The domination is total and completely invisible. At least, that's what happens on a default network. Let's rewind the timeline. This network administrator already configured the specific Cisco mitigations required to trap this exact sequence of events. As we see in this diagram, the moment the attacker launches their MAC flood, port security steps in. The administrator configured the port with a maximum of 2 MAC addresses and a violation action of shutdown. At the third spoofed address, the switch instantly air disables the port. The attack dies in milliseconds. When the attacker tries to spoof the IP pool, DHCP snooping blocks it. By classifying the lobby port as untrusted, the switch automatically intercepts and drops the rogue DHCP offer packets, bouncing them harmlessly off the perimeter. When the attacker attempts to poison the routing cache, dynamic ARP inspection kicks in. DAI is a security feature that validates ARP packets against a trusted database. It cross-references the incoming ARP packet against the DHCP binding table, realizes the attacker's MAC does not match the assigned IP, and deletes the spoofed packet immediately. These Layer 2 mitigations act as automated bear traps. They neutralize the initial chaotic wave of the attack with zero human intervention. To stop the attacker from jumping into the secure server segment, the administrator blocked VLAN hopping by configuring the port to switchport non-negotiate. They also explicitly tagged the native VLAN. This strips away the attacker's ability to ever form a trunk link. This animation shows the spanning tree defense. When the rogue Priority 0 BPDU attempts to hit the network, BPDU guard intercepts it. Because the packet arrived on an access port where no switch should exist, the port is air disabled, and the packet is frozen and shattered before spanning tree can even begin to recalculate. Finally, the web server's content security policy stops the phishing hook. CSP is an HTTP header that dictates exactly which scripts a browser is allowed to run. By enforcing a strict script source self-rule, the browser flatly refuses to execute the cross-origin beef script. On the attacker screen, the tools stall out. The terminal fills with connection refused warnings. Every protocol exploitation script fails instantly. The trap worked flawlessly. The attacker is entirely locked out of the hardware, and the network didn't drop a single legitimate packet. This diagram illustrates the ultimate takeaway for both your exam and real-world engineering: defense in depth. This is the strategy of employing multiple, independent security controls to protect a single asset. A single protocol will always fail in isolation. Port security stops MAC floods, but it cannot stop ARP spoofing. DHCP snooping protects your IP assignments, but it does absolutely nothing to prevent a malicious browser script. A truly secure network does not rely on a single impenetrable wall. It relies on a complete, overlapping system of specific attack and defense pairings, anticipating the breach and neutralizing it at every layer.